So today we're going to talk about the residual connections in case of transformer. So we all might have played a game of telephone where, let's say, there are n number of people sitting in the line and you whisper a secret to one person and then they whisper it to the next and then to the next to the end of the line. The original message over time gets completely unrecognizable. In deep learning, we have a very similar problem. So, in case of deeper neural networks, we have a problem known as vanishing gradients. So, when we try to make a neural network, like let's say 50 to 100 layers deep, the model would not just perform poorly, it would often stop learning entirely, right? So, this is basically the vanishing gradient problem. We'll talk about or see a small visual of what really happens. Yeah. So, this is a small visualization of what might happen in case of vanishing gradient problem, and we can have a look at it here also, right? So what really happens is that as the error signal travels backward and during the back propagation, it gets multiplied by small weights over and over until it shrinks to zero. The early layers, especially the early layers, they never hear the main juice, the main secret of what they wanted to learn, right? So this is basically the vanishing gradient problem. This was very common in deep neural networks. I think until 2015 we came up with something known as the idea of residuals. So in case of transformers, we had seen this idea, which is residual connections, right? So what we saw was that the model is adding the input to each sublayer's output. So in case of transformer, we are calling it sublayer. So one, we have attention sublayer, we have a feed forward neural network sublayer, right? So whatever sublayer we are at, we don't care. The output is not only denoted by y. So here y is being called as x plus f of x, right? Let's say this is the transformation that the sublayer has done, which is f of x. So what is the new output is nothing but x plus f of x. Okay. Whenever we thought about residuals or the term residual, how did we come up with this idea? So this means that every layer is not trying to learn the whole output from scratch. The layer's output says that I already know something. Okay, I already know something, or I know a lot of things. I am looking for that small residual f of x, right? The very tiny bit of extra information that I need to understand to and add it with what I already know. So if this information is useless, I can always zero it down, right? But if I mix this residual with my original information of what I know, I will make my output, right? So this is what really happens. I mean, on an abstract level, we can say that the gradients flow directly through the network and we are able to preserve signal and preserve more information from the earlier layers. But today we'll see what exactly generally happens, right? So if I try to Google, yeah, I think this is a fair image, or this image is worth noting, right? So let's say this is your transformation layer. You add the input, the output of this layer should be f of x, but now the output is denoted as x f of x plus x. In case of a transformer, let's also observe, we can see that in the yellow font we have mentioned the add here. So this is an encoder decoder architecture of one of the transformers that was mentioned in attention is all you need. So we can see that add and layer normalization. So add here is referring to adding the residual connection or skip connections, right? So f of x here denotes our residual, right? Not x is not the residual. F of x is the residual, right? Okay, so we can see that after attention also we added a residual, after feed forward neural network also we added a residual, right? So for every after every sub layer or after every layer we do add a residual. So what really happens is, so during the training time when we calculate how to fix these errors, right, or how to solve these errors or loss function during back propagation, we do gradient descent, right? So the gradient travels in back propagation through chain rule, and you know over time what really happens is, in case of gradient descent, if we are denoting a total y with x plus f of x, the gradient descent is going to differentiate it, right? So let's say if we are going to differentiate the loss function with respect to x, we will get this term, right? Because we have to apply chain rule. So lost dl by dy and dy by dx, right? So now what's going to happen is, we are going to not only compute the derivative of f of x, we are going to compute the derivative of the whole thing, x plus f of x. Now, if even if f dash x was supposed to be 0, or let's say if it tended to go towards 0, we still have an identity and a 1, right? That will get added to the derivative, right? So even if let's say this approaches to zero, the overall term, which is the derivative of loss with respect to x, is going to be nearly equal to derivative of loss with respect to y, right? It would not directly zero up, right? So I mean, this was the problem in case of gradient descent, or this was the problem in case of deeper neural networks. Every layer plus one used to take output of the previous layer, right? And we used to multiply them, right? And in but now what we have is we don't use this particular equation, right? Because this does not have addition of x. Now what we do is this, right? So what this basically helps us do is it takes in x together with f of x, right? So we have seen how it would favor in case of backpropagation, right? So 1 plus f of x, f dash x, is what is going to be multiplied now. That means we are not completely zeroing the gradient. The preservance of identity term is fundamentally changing the flow of gradient. That's why we also say that it stabilizes the overall training, it stabilizes the gradient flow. I also want to show you one research paper which had a very interesting case study. Yeah. So visualizing the loss landscape of neural networks, right? So this is what the loss landscape might look like, right? So this is the visual, I mean, this is one of the visual reasons that this also works. A lot of research has shown that without the residual connections, this rough loss landscape, the mathematical map of AI is basically very jagged, right? So the whole loss function landscape is very jagged, and it's also mountainous in nature, right? So we are trying to find the bottom of the whole mountain. It's super unclear. When we add residual connections, it smoothens out the whole landscape. If we so this is the 3D landscape. If even if we see the contours, the contour plot of both the landscapes, we would see a lot of difference, right? So it smooths out the whole landscape, and it also, in an abstraction, it also smoothens or stabilizes the training flow, right? So in forward pass, we have seen what really happens. In forward pass, this is what happens, right? So to every output f of x, we add in the layer's input. So xl is the input of the current layer, and f of x is the output or transformation of the current layer, right? So this f of x can come from multi-head attention, it can come from feed-forward neural networks, it can come from anything, right? So what we are trying to do is we are allowing to avoid the vanishing gradient problem. We are kind of preventing it, we are kind of stabilizing the training. This is also helping us in stabilizing our gradient flow, right? And we are also letting the model pass through a lot of information that it wants to preserve. So we're kind of preserving the signal, right? So, I mean, we can also say that it is kind of acting as a memory mechanism, and we are able to preserve the information by adding the residual and also preserving x. I mean, x and f of x together, right? So this is the mathematical nuance, and this is the visual nuance, and this is basically an abstraction nuance of the whole explanation. Like, why do we really need residual connections, right? So yeah. I think in the next videos we'll dive deeper into other nuances of transformers. Thank you.